So by simplifying, we'll get our PT value as 0.45%. So this is how we calculate the percentage of tension steel reinforcement. I hope you are understanding. So next we'll go for the calculation of the tau C by using the value of PT and SCK. So now we'll go for the calculation of the tau C by using the value of PT and FCK. So by using the help of these two values, we'll calculate the tau C value. For that, again we need to refer the table number 19 and page number 72. So we'll see table number 19 and page number 73, not 72, it's 73. This is a page number 73 of table number 19. So by using the value of PT and FCK value, we'll calculate the tau C value. So our PT value is how much we have got? 0.45. So why we need to calculate the percentage of tension steel reinforcement is this column. This column has the value of percentage of tension steel reinforcement. That's why we need to calculate the PT value. So our PT value we got. So we got how much? We got 0.45. We got. So look at here. Is there 0.45? So our PT value is 0.45. Where it comes? See here where it comes. It's not here on this row, but it comes in between the 0.25 and 0.50. It comes in between 0.25 and 0.50. So for 0.25, we have the concrete value, that is 0.36. For 0.50, we have the concrete value 0.48. So by taking this value and with the help of the interpolation method, we'll calculate the tau C value. So I will write down these values and I will show how to do interpolation. So for 0.25, corresponding value I have written here tau C value, that is 0.36. For 0.50, we have the value 0.48. For now we need to calculate the what is the tau C value for 0.45. So by doing interpolation method, I will show how to find out the tau C value. The tau C is equal to 0.36. The least value I am taking 0.36 plus I am adding it. So why I am adding means this value goes on increasing. So that's I am adding it. Plus 0.48, the greater value minus least value, divided by greater value minus least value. So 0.48 minus 0.36 and 0.50 minus 0.25 into the value which you want to find, that is 0.45. 0.45 minus the least value, which is least, 0.25 is least. So 0.25. So simplify this, we'll get our tau C value as 0.45 Newton per mm square. So this is how we do the interpolation. So next step is to comparison of tau C and tau V. So whatever the value we have calculated, so let's compare. So our tau C value we got is 0.45 Newton per mm square, and our tau V value also we got is 0.45 Newton per mm square. So both the values are equal. So when our tau C equal to tau V, or when our tau V is equal to tau C, we should provide the minimum shear reinforcement. The shear reinforcement is carried by concrete. So we need to calculate the spacing of stirrups. So spacing of stirrups should be calculated. For that, again we will go for the codebook rule. So what it says, for the calculation of spacing of stirrups as per IS 446-2000, cos 26.5.15 and 26.5.16 on page number 47 and 48. What it says? So as per cos 26.5 1.5 and 26.5 1.6. So we'll see what it says. So this is the page number 47. The maximum spacing of shear reinforcement. The maximum spacing of shear reinforcement measured along the axis of the member shall not exceed 0.75 d for vertical stirrups. So what they have mentioned, the spacing of stirrups value should not be greater than 0.75 d for vertical stirrups, where d is the inclined stirrups, and D for inclined stirrups at 45 degree, where D is the effective depth of the section. So in no case shall the spacing exceed 300 mm. So what they are saying? They have said a spacing of stirrup should not be greater than 300 mm. And there is one more criteria. So minimum shear reinforcement in the form of stirrup shall be provided, such as by using this formula will provide the minimum shear reinforcement. For that we have the formula SV divided by B into SV is equal to, this not greater than or equal, this is equal and equal to 0.4 divided by 0.87 Fy. So by using this formula we will calculate the minimum shear reinforcement. And there is what they have mentioned. Number 1 is our spacing of stirrups should not be greater than 0.75 d, and number 2 is our spacing of stirrups should not be greater than 300 mm. And so we'll see how to calculate this step by step. So the same formula which is given on page number 48 I have written here. So now we are calculating the spacing of stirrups. For that I have rearranged it. So SV is equal to 0.87 Fy ASV divided by 0.4 into B. Have rearranged it for calculation of SV. So now, we know the value of Fy and B, and what is unknown here? ASV is unknown here. So for that again we need to assume the number of pi bars, that is 2-legged vertical stirrups of 8 mm pi bars I am assuming. So to find out the ASV, so ASV is equal to 2 into pi by 4 into 8 square, that is diameter. I have taken 8. So substitute all the value. After simplifying we'll get our ASV value as 100.53 mm square. So now substitute ASV value in this equation. So SV is equal to 0.87, our Fy is 4 and 5, our ASV which we have got is 100.53, 0.4 into B value is 200 mm. So substitute all the value. So simplify this, we'll get our SV value as 453.70 mm. So this is the first criteria. We'll go for the second one. So they have also said our spacing of stirrups should not be greater than 0.75 d. So SV is equal to 0.75 into d. How much we have got? We have got 250. So substitute all the values. Simplify this. We'll get our SV value is as 187.5 mm. So I am making it into 175 mm. So number 3. Third criteria is SV should not be greater than 300 mm. So that's why I am taking SV is equal to 300 mm. So they have also mentioned the spacing of stirrup should be least of these three. Our SV value should be least of these three. So which is least? 175 mm is least. So I am taking SV value as 175 mm. So whenever you are calculating spacing of stirrups, if you get less than 300 mm like 175, 150 or 250, at that time you can provide whatever you got, the less value. but in sometimes if you get more than 300 mm, that is nothing but 350, 380, 400, 500, like that. At that time you should provide the minimum value, that is 300 mm. So I hope you understood. This is how we calculate the SV. So I am taking the least value SV is equal to 175. So I am taking SV is equal to 175 mm. So provide two legged vertical stirrups of 8 mm bypass at 175 mm center to center. This is how we calculate the spacing of stirrups. And the last step is to check the deflection control. This is the last step of our problem. So for that what we have to do is, again by using codebook, by using figure 4 and page number 38, and by using these two we'll see what they have given on page number 38. This is the page number 38 of figure 4. Page number 38 figure 4. So this is the chart. By using this we'll calculate the FS value. We'll calculate the, not FS value, we'll calculate the KT value. So by using the value of percentage of tension, reinforcement, and by using this FS curve we'll calculate the KT value. So now before coming to this chart, there is one formula they have given, that is Fs is equal to 0.87 Fy area of cross section of steel required. So Fs is equal to 0.87 Fy area of cross section of steel required divided by area of cross section of steel provided. So by using this formula we need to calculate the Fs. To find out the KT value, modification factor, we need the value of Fs. So in this chart contains the value of Fs curve. So that's why we need to calculate the Fs by using this formula. We'll see. So after calculating Fs value, by using Fs value and our PT value, we'll calculate the modification factor. So I will show. So I have written the same formula which is given on page number 38. Fs is equal to 0.87 Fy into HT per required divided by HT provided. So substitute all the value in this formula. 0.58 into 4 and 5 HT required we got is 222.64 divided by HT provided we got 226.18. Substitute all the value. So after simplifying we'll get our Fs value as 236.93 Newton per mm square. So now by using this Fs value and our PT value, we'll find out the modification factor by using that chart. So by using Fs value and PT value, we'll find out the modification factor. So our Fs value we got is 236. So 236 means it comes near to this curve 240, Fs 240. It comes near to this curve. So by using our PT value, we got our PT value as 0.45. So 0.45 means it comes in between 0.4 and 0.8. So it comes here middle of the this line. Wait, I will show. So it comes here 0.45. So straight to this, and where it touches the curve and left to this, straight to this is our modification factor. So our value touches here and straight to here is our modification factor. It comes approximately 1.3, just above the 1.2. So it comes here. It comes approximately 1.3. So this is how we calculate the modification factor. So our KT value we got is 1.3. So 1.3. So next step is to go for the deflection control. So if you remember the formula which have shown by the calculation of the effective depth L by D ratio, so I will show again. So from page number 37, for simply supported beam, they have said L by D ratio should not be greater than 20. So by applying this rule, we'll calculate the deflection. So I'm taking our L by D as 20. So L by D max is equal to 20 into modification factor which we have calculated, that is KT. So 20 into 1.3. So substitute all the values. By simplifying, we'll get our L by D max value as 26. So next our L by D provided. So L we got is 3200 and divided by D we got as 250. Substitute all the value. After simplifying, we'll get our L by D provided as 12.8. So by comparing these two, which is least, so our L by D provided is least compared to these two. So our L by D max is greater than L by D provided. So NC deflection control is okay. So this is how we calculate the deflection control. So for this, to check off the deflection control, we need to calculate the modification factor, that is KT. For find out the KT value, what we have to do? We have to calculate the FS value. So this is how we deflection control is deflection control is calculated. So this is the last step of this problem, and the next step is to drawing of reinforcement details. Without the drawing, the problem has no value. So we'll see drawing reinforcement details of this problem. So this is the drawing of our beam. So these two are the support of 200 mm. So having the effective span, so effective span of 3200 mm and clear span of 3000 mm. The overall depth of beam is 300 mm. So these are the two laid vertical stirrups of 8 mm pi bars at 175 mm center to center. This is the hanger bar to support the vertical stirrups. We have provided hanger bars, 2 numbers of 10 mm pi bars, and this is the main bar. At tension side, we have provided 2 numbers of 12 mm pi bars, and these are the vertical stirrups which you are seeing. And this is the longitudinal sectional diagram of our beam. So when you cut the beam here or at the middle, what you are gonna see is, you are gonna see 2 numbers of 12 mm pi bars at tension side and 2 numbers of 10 mm pi bars at top side, and the red line which you are seeing is 2 legged vertical strips of 8 mm pi bars at 175 mm center to center. This is the overall depth, that is 300 mm. So width of the beam is 200 mm. This is the cross section diagram of our beam. So this is the reinforcement details of this problem. I hope you guys understood. So if you like the video, so like it, share it and subscribe for the more videos. Thank you for watching.